have Larry Nittler visiting us. He's going to talk about this word, which we'll explain. It's an interesting history. He's from, as you see, Carnegie Institute of Washington, actually in Washington, not the one in Pasadena. So it's extending our links with the Carnegie Institute of Washington. He's a cosmochemist, that's the word generally described him, which means he studies bodies in the solar system, the chemistry of them, both in situ and with meteorites on the ground. He gives a very nice talk on the links between meteorites and the kind of astrophysics we normally study. So that would be a good colloquium if you could come and give that sometime. But today he's especially going to talk about the X-ray fluorescence spectroscopy of the surface of this rocky body, because we're wondering if there's a place where our instrumentation developed here could be applied to this kind of work, which would be a new thing for most of us, but not for Paul, of course, Paul Gorenstein, who's been doing this for a long time. So this will be fun. Larry is a recipient of the Alfred Neer Prize for the Meteoritical Society, and he's a fellow of that society also, which is an honor. And he has an asteroid named after him, 5992 Nittler, which is a much lower number than mine, which is very annoying. Okay, so no more ado. Do tell us about hermeochemistry.
Okay, thank you very much for the introduction and for inviting me up, Martin. It's a pleasure to be here. I've had many questions about hermeochemistry. This actually, I should say that I got into this remote sensing business around 2000, working on the near-Earth asteroid rendezvous mission to the asteroid Eros, and learned this field from Paul Gorenstein, who was on the science team. And when we were writing our first paper on results from the X-ray instrument on that instrument, we sent it to Science, and the editor at Science objected to our using the word geochemistry for a body that wasn't the Earth, because she strongly felt geo meant Earth. And so I suggested erratochemistry, since we were around Eros, and she backed out and said geochemistry was okay. But in any case, just in case she was still around at Science, I decided at the beginning to, when we got involved with Messenger, to coin the word hermeochemistry for the composition of Mercury, which of course is Hermes in Greek. But so that's the origin of that word. But then the PI of the mission wouldn't let me use it on that science paper either, so I just use it in talks occasionally. But I'm going to talk, this is, as many of you have probably heard, Messenger's a NASA mission that just ended 4 very successful years in orbit around the planet Mercury. A few weeks ago, enormous trove of scientific results. I'm going to focus here on the chemical measurements that we made with atomic and nuclear spectroscopies. But before I get into that, since this is a astrophysics talk and I'm talking about planets, I'm going to talk about planets. Mercury, of course, has been known to humans as long as humans have been looking at the sky, because it's one of the few naked eye planets. But many people, of course, have not seen it because it's very difficult to see. It's always low on the horizon, just before or after sunset, because it's close to the sun. I'm going to skip a few slides. There were historically observations throughout the development of astronomy, even back to the prehistoric times. There's a recorded observation from Mesopotamia. But the early days of astronomy, people started building telescopes, discovered Mercury had phases, and in the late 1800s, early 1900s, people started drawing maps. Lowell found lots of canals all over it. That sets a theme. But the point is that most of this ground-based work was not very useful into the modern age, just because it's difficult to observe Mercury. It's so close to the sun, you can't point big telescopes at it generally. Hubble can't point that close to the sun. It's just a picture of a Mercury transit. And it's very difficult to visit by spacecraft, because you're falling into the gravity well of the sun if you try and go there. So you have to fight the acceleration from that if you want to get down and spend any time there. So the only spacecraft to visit Mercury before Messenger was a mission called Mariner 10 that did 3 short flybys in the mid-1970s. And until Messenger, that was the only spacecraft visit to Mercury. And a lot of what we know about Mercury was, of course, from those 3 flybys. And in fact, those flybys unfortunately flew by the same side of the planet all 3 times. So they only imaged about half of the planet at high magnification, but this is a mosaic of one part of the planet from the imagery from the 70s. but made the very important discovery that Mercury had a magnetic field, which is the only other planet in the inner solar system with its own magnetic field, which leads to very interesting space physics of the interaction of its field with the solar field and the solar wind. Also detected that it had a very, very weak exosphere, not an atmosphere, but some atoms coming off the surface. But in the meantime, ground-based astronomy did do some very important work, and largely by radio astronomy, but also optical astronomy. One important discovery was in the 60s is that it's in this 3-2 spin orbit resonance, which means it spins 3 times on its own axis for every 2 times it goes around the sun. So many people, I find even people today think that Mercury is in some sort of tidal lock thing with the same side facing the sun all the time, but that's been known not to be true for 50 years. But in any case, it is in this very unusual resonance. Also discovered from ground-based optical astronomy emission lines of sodium, potassium, and calcium in the exosphere. So we already knew some of these elements were present at Mercury. A very important discovery, I'll get back to this later, was from Arecibo observations, radar observations in the early 90s, discovered that materials in deep polar craters, impact craters near the Mercury's poles, had this bright radar reflective material that looked like water ice. And so the idea it's postulated that there are deposits of water ice in deep craters that never see the sun, that are in permanent shadow. And one of the goals of the MESSENGER mission was to test this hypothesis. And also, just by very, very careful observations of Mercury's orbit and its librations as it wobbles around during its rotation, geophysicists were able to determine from ground-based measurements that Mercury's iron core, the outer portion, is molten and causes slight, subtle shifts in the way it wobbles that we were able to tell us that even before we got there with MESSENGER. But MESSENGER, well, I'll get there. So Mercury, why do we care about Mercury? Well, we care about everything. We want to understand our solar system. But Mercury is quite important. It's the smallest, densest planet, and it's the closest to the sun. We like to say it's an end member of planet formation. It really, we know the planets formed by some common process in the protoplanetary disk that made our solar system, but we don't know, we don't understand many of the details. But in many ways, Mercury is one end member of this whole population of things. It's got some extreme values. It's also just interesting from a planetary point of view of the environmental extremes. It's very hot, it's very cold. It's also very, very dense. We don't understand this. Its core makes up a much larger fraction of the planet than it does on the Earth, for example. It has this magnetic field, which is unusual for a small planet that's not geologically active. So there's a lot of mysteries, and but it's clearly of importance if we want to understand our solar system, to understand the properties and origins of the various planets. And it's also important when we start thinking about extrasolar planets, in that, of course, this is now, as of, a month or two ago, a plot of the known exoplanets around other stars. And what we see is Mercury, in terms of its semi-major axis and eccentricity, is actually fairly typical for planets. It's much less massive than many the known exoplanets, but in some ways it provides some context for understanding the planets around other stars in terms of where it is in its orbit. So MESSENGER, which brings me to MESSENGER. MESSENGER is the first spacecraft to ever orbit Mercury, only the second spacecraft to visit it. It was the 7th in the line of Discovery-class missions that NASA instituted starting in the 1990s. That are faster, better, cheaper, low budget, PI-driven, relatively rapid timescale planetary missions. The PI was Sean Solomon, who was formerly my boss, the director of my department at Carnegie. He's now the director of the Lamont Doherty Earth Observatory at Columbia University. But he successfully submitted this proposal in around 1998, 1999. It was selected, which is exciting. It's very difficult, as I said, to visit Mercury by spacecraft. And one problem, of course, is it's hot. And you're flying close to, relatively close to the sun. Now, it's not a solar mission or a solar probe where you're trying to fly into the sun or whatever these things are. But you want to spend some time at this planet, you want to last a while. So one way we deal with the thermal problem is the whole spacecraft was behind a giant ceramic cloth sunshade, which was always kept between the spacecraft and the sun. So that protected us from the sun. sun's heat, and also the solar panels were actually mostly mirrors to reflect the heat away. And both of those were very, very good at protecting the spacecraft itself. It stayed, even though incredible radiation on this side, it stayed very, very cool on the other side, except for the problem of the reflected heat from the planet. I'll get back to that in a minute. As I also mentioned, it's hard to get to Mercury because we're falling into the gravity well of the sun, but people much, much more clever than myself came up with ways to do this, and it involves 7 or so gravity assists to basically, and 7 years of cruise in order to get into orbit. So we launched in 2004, flew by Earth a couple times, Venus a couple times, and then 3 flybys of Mercury before we had basically given up enough momentum that we could do one controlled engine burn and get captured by Mercury's field. And like I said, it took about 7 years, but it was extremely successful. That's a picture of the spacecraft during a vibration test before launch. Those are human beings for scale, so that kind of gives the scale of the thing. Beautiful night launch in August of 2004, very successful. There's a couple pictures its camera took on the way. Flew by Earth, by Venus a couple times. And we flew by Mercury 3 times in 2008 and 2009. So already before we were even in orbit, we doubled the amount of time the spacecraft visited Mercury. And as I said before, Mariner 10 had imaged about half. With just these 3 flybys, we then imaged about 90%, had imaged about 90% of the surface even before we got into orbit. And these are pictures from these 3 flybys. Even from this, there was a great deal of scientific results. There was evidence that there had been volcanism, which had been a matter of great debate for decades. There was interesting color and albedo variations that hadn't been seen before. Again, we clarified more issues with the magnetosphere, discovered that the exosphere is variable. So there were important scientific discoveries, but it was really just sort of an appetizer because we knew we were going into orbit and we'd have a lot more time. And in fact, March 18th, we went into orbit. And I just wanted to show this because it's very important to understand that we were in a very, very elliptical orbit. We were in a polar orbit. So we would fly over the North Pole, zoom in, have a quick look over the North Pole, say until towards the end of the mission, we were always, our periapsis altitude was usually about 200 to 500 kilometers. And then we'd fly out to about 15,000 kilometers over the South Pole. This is the way we deal with the heat. So our instruments would heat up from being reflected light from the surface of the planet, and then we'd have 8 hours to cool off and go back down. The first year we did 12-hour orbits, and then after that we switched to 3 8-hour orbits every day. But what this means is our best views were always over the northern hemisphere, and that's where our instruments have better spatial resolution, that's where we're close, and the southern hemisphere much less so. But the other thing is you can consider each one of these almost a flyby because we're so far out here. So in some ways, so in any case, before we crashed into the planet a few weeks ago, we completed 4,104 orbits. So it's a lot of orbits. And I should mention that it actually took 2 years of orbits to get from that 90% to 100% coverage. It's always, that last little bit is hard. We finally covered, so we have images of the entire planet. That's the North Pole, which was some of the hardest, maybe that's the South Pole. I can't remember. I think this is the South Pole, and that was where we had to film this. In any case, that's what Mercury looks like. This is, before I get into the geochemistry, I just love this picture because it's a nice view of what Mercury looks like in approximate true color, what it would really look like if you were sitting on the spacecraft looking at it. And what it looks like is the moon. It's gray, it's covered with impact craters, kind of dark and okay. I think it's beautiful. But of course, many people thought for a while, we're thinking, it looks like the moon, it's about the same size as the moon. There were many papers beforehand that postulated it was more or less the same as the moon. Well, it's not like the moon in any sense, except that it's dark and gray and covered with impact craters. This is now, okay, this is a nice view that I have to play the movie separately. And so this is now a global movie where we've applied a principal component analysis to the, that's a movie for later. So that idea of running the movie outside didn't work. I fried my laptop over the weekend, so I had to borrow a laptop here, and of course, movies never work when we run them on someone else's computer, so I'll just come back to this and mention that you saw it. Ah! Hell is using someone else's computer. Ah! Okay. Stay back. The point is that this is a false color representation that, based on a mathematical deconvolution of the color imaging, that brings out really subtle color differences and brightness differences in the planet. And so this tells us that even though it looks just boring and gray, there's actually some significant differences here. We could tell just from the color data that there's large regions that are oranger in this representation, and large regions that are bluer and darker. And a key question was, what do these mean in terms of the origin, composition, and history of this planet? So that's sort of an overview of what the planet looks like and how we got there. I should mention that Messenger was designed with a number of guiding science questions. That's, of course, how you sell a proposal. Convince NASA that you're going to answer all these important science questions, and we have, or we've tried to. But the point is that we have a whole set of guiding science questions that the mission was designed to answer to better understand Mercury, and these were tied to specific measurement objectives in various ways, and then a scientific payload was designed to address these. And I'm going to focus here on this very first measurement objective, which is mapping the elemental and mineralogical composition, and specifically the elemental composition of Mercury's surface. This is the payload of the spacecraft. It was extremely successful considering the relatively low-budget discovery mission. We had cameras, a laser altimeter, various plasma instruments, but I'm going to focus here on these instruments: an X-ray spectrometer, which is here in the solar monitor part of that, a gamma ray spectrometer, and a neutron spectrometer, because these are the devices we can use to measure the actual elemental composition of the surface of the planet, which is very, very valuable for understanding how it formed, what it formed from, and so on. So I'm going to now jump to what my main role has been, and which will be the main focus here, which is the X-ray spectrometer, and which is why I'm here, because there's so much interest in developing better versions of this kind of instrumentation here. The basic idea behind X-ray, planetary remote sensing X-ray spectroscopy, is that you have a source of X-rays in the solar corona that shine on the surface of your airless planet or body. Those knock electrons out of atoms, which then rearrange themselves and emit fluorescent X-rays that can be detected by the orbiting spectrometer. No, it's the same concept as a laboratory X-ray fluorescence instrument, except that in the lab you have an X-ray source that you control and understand and really have well calibrated. In the laboratory you have a fixed geometry, and in the laboratory you have standards that you can measure, elemental standards, so you can quantify the data. This is a much, much more difficult problem when you're doing it remotely in space, and depending on a source like the sun, which the X-ray spectrum is changing in both spectral shape and intensity on a minute basis or time scale. And so this is difficult, but we've this is pioneered in the Apollo days, and it works when you do it right. And so this is just a schematic of the instrument. It is very similar to the instrument that flew on Apollo 15. It's a set of 3 gas-filled proportional counters. This is not state-of-the-art X-ray technology. And gas proportional counters have very, very bad energy resolution. They're not modern solid-state detectors, and they very clever design for this. And I don't know, was that Jack Trumka or Izzy Adler, or who came up with the balanced filter approach? Was it you?
Some of us at ASB also.
Yeah.
Conjunction with Jack and Izzy.
Yeah. Anyway, long before I was involved, came up with a very clever way to come up with energy resolution when you don't have energy resolution in these detectors. And first of all, I should say there's beryllium copper collimators on the surface that collimate the field of view to 12 degrees, which gave us a spatial resolution ranging from, at the very end of the mission, a few kilometers, but typically the best resolution during the mission was maybe 100 kilometers or so, up to several thousand kilometers when we were looking at the South Pole. But we did have spatial resolution, and I will show maps. This idea of balanced filters is that you have these three counters, and in front of one of them you put a thin bit of magnesium foil, in front of another one you put an aluminum foil, which differentially absorb the X-rays at these low energy regimes. So if you have magnesium, aluminum, silicon, fluorescent photons hitting the detector, they get absorbed in different amounts in the three detectors, and you have a matrix, essentially a matrix deconvolution problem to solve. And you can end up, from measuring the signals in the three, deconvolve and get what the initial fluxes of those lines are, even without being able to actually resolve them in any given detector. And this works very well. As I mentioned, the actual analysis, the spectrum you measure depends critically on what the incident spectrum is, and that's the solar spectrum, which is changing constantly. So we also had to have a detector pointed at the sun, and it was just called SATS, and there's a silicon diode, just a little silicon diode behind a beryllium window with a pinhole in it. And it worked, and I'll show you the spectrum in a second. The key point here is that without standards, you have to use modeling and fundamental laws of physics to convert the signals you detect to composition, which is what we're interested in. And the actual signal you get in a given fluorescence line depends on the shape of your incident spectrum. It depends on the actual composition, so on the total composition. So how much silicon fluorescence you get will vary depending on how much magnesium and iron and other atoms there are in the surface, because they can absorb X-rays coming in and out and have a big effect. And it also depends very much on the geometry of the situation. And you also have to worry about not just fluorescence, but the reflected scattered solar spectrum coming back into the detector as well. So, okay, this is another movie. This is to show how sensitive we are to this kind of thing, only the movie doesn't work. But I'm going to try again without going, I need that, or so you told me.
Yes.
And X-ray specs, okay. So what this is, oops, we come back, is I'm just going through a day of time, and that's just sort of the count rate in the solar monitor detector, the solar spectrum, and the fluorescent spectrum we're getting from the surface. And I wish that would go away. And what you can see is every now and then you get a big flare, and the counts rates go up, and the spectrum changes. Okay, this isn't working as well as I thought, because it was before incorporated into the PowerPoint. Okay, I can't pause it. I think there's one more. So you can see as the solar spectrum, solar count rate gets higher, the shape of the spectrum gets flatter, gets harder, and you start getting fluorescence from heavier elements like calcium and iron. And during normal time, you only get sort of stuff down at the low energy. And this is just to show how variable it is with time, how in order some elements require solar flares, some elements do not. It's all very complicated, but we do it. Now where did that go? But here's an example of flare during a large solar flare. This must have been at the end of this particular thing. And you can see in this solar flare we're detecting emission from iron complex in the solar corona. Yeah?
How long is that?
This might be a day's worth of spectra. I don't remember. I made this a couple of years ago. But this kind of variability could be a few hours or a day. And you can see under these conditions, we're seeing very strong fluorescence from magnesium, aluminum, which is in between silicon, sulfur, calcium, and even some iron. So we really like these solar flares because they provide the most information. But of course, they don't happen all the time. In any case, to get the data, we've had to do all kinds of modeling and spectral fitting, as people in this room are very familiar with doing this kind of thing. And for example, we use a Chianti solar model to calculate the spectrum of the solar corona that matches our observation. So the observation here is the blue, and the green is then the theoretical model that, going through the response of the detector, matches the spectrum. And then we can use this high-resolution spectrum, theoretical spectrum, as an input to models fluorescence from the surface of the planet in order to determine it. So we do this iterative approach where we fit the planetary spectra to forward models where we just vary the abundances and predict synthetic spectra that we then match to the observed spectra until we get a match. And here's an example. So these are our 3 different detector spectra during a flare, and we have to simultaneously match all 3. And again, the shapes are different at the low energies because of these balanced filters. And in the end, you can do this and say, in order to get this good fit, you have to have 25% silicon and 12% magnesium or whatever. And in this way, we've been able to fit thousands and thousands and thousands of spectra over the 4 years of the mission and do elemental abundances. The other methods I'm going to talk about a little bit that we've used for composition are gamma ray and neutron spectroscopies. And these are now nuclear spectroscopies where galactic cosmic rays hit the surface of the planet. They undergo nuclear reactions with the atoms or the nuclei that are present, produce neutrons, which can be captured by other elements and release gamma rays if they're in unstable states. These neutrons can interact in various ways that produce gamma rays with characteristic energies of specific isotopes or elements. And of course, we can also measure gamma ray decays directly from natural, or gamma rays from natural radioactive decay from elements like potassium, thorium, and uranium. So some elements we can measure directly, others are indirectly. The gamma ray spectrometer was a cooled germanium detector. So it had this thermoelectric cooler, a thermomechanical cooler that kept it at whatever temperature it was because you need it very cold. It also has a shield, a plastic shield around it, which was used originally as an anti-coincidence shield so we could veto events that were coming from galactic cosmic rays hitting the side of the detector, so that we would only count gamma rays coming from that direction as signal. And then, of course, it produces light that's detected by a photomultiplier tube. But it was very, very successful, but about 1 year into the mission, the cooler died. This was within its anticipated lifetime. We hoped it would last longer, but it failed. And at that point, we couldn't use the gamma ray spectrometer anymore, but a little while later, about a year later, we repurposed this plastic detector, this plastic shield, as a neutron detector. So we had a separate neutron spectrometer compared to the other neutron spectrometer, which is probably up next. Oh, okay, there's a Mac PC thing. We'll skip that. So I'll get back to the neutrons later. But the gamma ray, here's an example of gamma ray data. This is from early in the mission. And of course, there's huge background of gamma rays there's a huge background of particles in the detector, even when we veto a lot of them. There's also a huge background of gamma rays that are produced in the spacecraft. And so you see all these high altitude means we're very far from the planet. There's no chance of any actual signal from the planet. And you can see all these characteristic lines in gamma rays, and these are definitely just due to impurities in the detector or elements in the spacecraft interacting with cosmic rays. The black curve now is the spectrum much closer to the planet. And one thing you can see, for example, is there's an obvious difference here than here. And so, of course, what we have to do is compare the low altitude to the high altitude data, and from that we can determine abundances, and there's all kinds of, it depends on the element and how you do it, but you can end up resolving these peaks and fitting them. And just as with the X-ray spectrometer, a lot of it involves a lot of forward modeling and nuclear cross-section, nuclear reaction simulations in the planet to predict the signal you will see and then compare it to what we get. But it seems to work. The radioactive ones are much more simple because they're just radioactive decay, so you can really just count the photons. The neutron spectrometer, I don't want to get into much detail. I'm only going to talk about it a little bit. But it's essentially a sandwich of two different a plastic scintillator with two liquid or lithium glass scintillators. And this is very sensitive across a very, very wide range of neutron energies. And then, as I mentioned, we also made the gamma ray detector into a neutron detector after the cooler failed. So we have some interesting neutron data from both instruments. So that's the methods and the instrument. I want to talk very briefly about the number one science goal of the mission is to try to understand why Mercury formed with this very large iron core. Why does it have a larger amount of iron in its bulk composition than the other planets? Especially given that we understand, or we believe, that terrestrial planets all formed by the same general process of accretion, this hierarchical position where you start with a disk of gas. As it cools, the gas atoms condense into dust. The dust grains collide together to form rocks, to form planetesimals, and finally form planets. Now, every stage in this is poorly understood, I would say, at this point. And there are big barriers in our understanding of how you go all the way from dust to planets. But we think this is the basic process. And the four terrestrial planets, form fairly close to each other on the scale of the solar system. And so why is Mercury so different? And chemistry is key to testing models and ideas about this. And part of this is that if you look at some of the models that were proposed for many years, some of them, they all will have effects on the starting, or the chemistry, the composition of the resulting planet. And so some ideas early on, before MESSENGER, going back in some cases to the 70s, were that Mercury accreted very early at very high temperatures in the solar nebula and produced iron when all the iron had condensed as metal, but a lot of the other elements hadn't condensed into dust yet, and therefore had very high iron in it. Another idea pushed by Al Cameron was the idea that Mercury was essentially close to an early active sun, and it formed much larger, as a much larger planet with a core to planet ratio much similar to the Earth, and then much of the pre-existing crust and mantle got evaporated off early on. A related model that's still popular is from George Weatherall and from Willie Benz, is that it started much larger and something hit it. Just like we think formed the moon in our system, it's possible that Mercury formed much larger. It got a very giant impact that knocked much of what was pre-existing off the surface, and in such a way that it didn't come back down on the surface. And then another idea going back to the 70s is that you could have some sort of physical fractionation in the solar nebula, in the solar disk, that separates metal from rock and concentrating the metal close to where Mercury formed. So all of these were ideas, and what can we say about them? Well, let's look at the actual data now. And probably the most important chemical discovery we made on Mercury is that it's very rich in volatiles. And so this is now gamma ray data. This is Mercury, our best result for the potassium and thorium bulk abundance of the surface of Mercury. And these elements are very important as tracers of volatility because they behave very, very similarly geochemically on a planet. So when the part of the mantle melts and forms a lava flow on the surface, the potassium and thorium, the relative amounts of potassium and thorium will be the same in the rock at the surface as in the bulk planet. So we think the surface measurement is characteristic of the bulk planet. But potassium is a very volatile element, and thorium is very refractory. And so what you can see here is Mars, Mercury, and the Earth all lie up here with a relatively high potassium and thorium ratio. The Earth's moon is much, much lower, more than a factor of 10 lower than the Earth. And this is thought to be a direct reflection of the giant impact that formed the moon. That heated the material and it lost potassium relative to thorium before it coalesced to form the moon. Mercury doesn't show any sign of that. It seems to have the same potassium budget as the other terrestrial planets. We have a paper just coming out in Icarus in Press that with a similar result for chlorine. We've now found that from the gamma rays that Mercury has a high abundance of chlorine. We also know it has a lot of sodium, and all of these in abundances similar to the other terrestrial planets. And so I'll come back to that in a second. In terms of major elements, this is the main work of the X-ray spectrometer, and this is now data we published in Science in the first year of the mission, and the basic picture hasn't changed except that we have a lot more data. And the basic point is here that this is a plot of magnesium silicon versus aluminum silicon and calcium silicon versus aluminum silicon. The red points are Mercury, and The range on Mercury now is a little bit broader, but not that much. And what's key to notice here is that Mercury, the Earth's crust is right here. The moon are these green points. Mercury is magnesium-rich and aluminum-poor and calcium-poor relative to the lunar and terrestrial crust. So we can already tell it's different. There's no hint of this very high aluminum-rich rocks like you see on the moon, which are thought to be the form of a flotation crust from a magma ocean, that the moon was completely molten, and the first minerals that crystallized out of this magma ocean were light aluminum-containing rocks that floated to the surface and formed the lunar highlands. Clearly, there's no evidence for anything like that remotely on Mercury. The other thing I wanted to point out here is this is the result from the gamma-ray spectrometer, and it agrees perfectly with the average of the X-ray data. This is very important because, as I mentioned, unlike laboratory measurements, we don't have standards. The experiments are not very well controlled. There's a lot of modeling and assumptions that go into the quantification of these data. The fact that these two techniques that are fundamentally extremely different have their own sets of systematic biases, different sampling biases, get the same answer gives us some confidence that we know somehow what we're doing. So this is, this movie actually works. So as I said, that was the beginning of the data mission. If I go back to that, we had maybe a dozen measurements of different spots on the surface. We now have, after 4 years, have managed to make maps of the entire surface of the planet for magnesium and aluminum, normalized to silicon. And the spatial resolution varies. As you can see, we have very little spatial resolution in the south, very good spatial resolution in the north. It's required some development of some new methodologies in order to make these maps out of measurements that have different spatial resolutions and different uncertainties. What we see is some very interesting variations in these abundances across the surface. These are telling us something about the geological history. There's this large region that's much, much more enriched in magnesium and poor in aluminum that we don't see elsewhere on the planet. We don't fully understand this, but we think it might be the remnants of a very, very old impact basin that might have exposed some mantle material. So the point is that this is the first time that X-ray fluorescence spectroscopy has been used to map the composition of an entire planet. And it is very successful and very powerful, and clearly should be used more in other places. The other important discoveries we made with the X-ray spectrometer was we confirmed that the overall abundance of iron was low on the surface. We knew it, we had suspected it was, and even though the planet itself is iron-rich, the iron on the surface is very, very low, up to a couple of weight percent at the maximum point. Sulfur is one of the big surprises of the mission. We discovered that there's several weight percent sulfur on the surface of Mercury. So in comparison, the Earth's crust only has a few hundred parts per million of sulfur. So Mercury is a very, very sulfur-rich and iron-poor planet relative to the others. It's also rich in volatiles, as I said. This composition indicates that Mercury formed under much less oxidizing conditions than the other planets. Essentially, it has less oxygen relative to the other elements in its bulk composition. We don't know why this is, but it's an extremely important data point for understanding the formation of all the terrestrial planets. In addition to the maps we've been able to make with the X-ray spectrometer, a couple potassium count rates were high enough from the gamma rays to make a coarse resolution map and show some significant heterogeneities in the potassium across the surface. This is all in the north. And this is a very recent paper where the mapping the flux of neutrons, low-energy neutrons from the surface of Mercury using this repurposed gamma ray shield. And what we see, again, are some very big differences, variations in the flux of neutrons. And this is the Dolores Basin, which is the largest impact basin, and it showed up as different in the other maps. I should have pointed that out, I'm sorry. This is this region that's so magnesium-rich. It's also interesting. So the point is this is now yet another technique indicating that there are chemical heterogeneities across the surface that are clearly of scientific importance. So to sum up the chemistry, Mercury is essentially what we have learned from 4 years of orbits is that Mercury is a volatile-enriched, chemically reduced planet. This rules out a bunch of these pre-messenger formation models I mentioned, like high temperature accretion, evaporation of the mantle of the sun, because all of these models predict loss of volatiles, predict that these high temperature models predict that Mercury should be very, very depleted in volatiles. And in fact, it seems to have as high or higher volatile inventory as any of the other terrestrial planets. But it has this different oxygen abundance, and we don't really know what that means. This idea of this hypothesis of forming Mercury by stripping a larger mantle by a big impact is still viable, but it's viable because no one's done the modeling right to make any geochemical predictions. And so we don't actually know if it's possible to strip off that much of Mercury, remove all that material, and still have the remaining Mercury as rich in volatiles as it is, because no one's done the combined geochemical modeling. But Sarah Stewart most recently left Harvard for UC Davis, is working on some of this modeling, and I'm hoping she gets some results soon. But the key point is that Mercury is clearly made of a somewhat different mix of materials than the other terrestrial planets, and that has to go into any full model of understanding the accretion of the solar system. So I'm actually doing well on time. I just want to talk about a few more things, just a few more science results. I cut out most of what I could have talked about because I wanted to focus on the chemistry, but just some more pictures. One of the main science results of Mercury is that Messenger is that the surface is made by volcanism, and we see all this evidence of channels, and lava channels, and vents from explosive volcanism. This is a large region of the northern polar region that's roughly the size of the United States that is one giant flow of lava. However, what we found from the chemical measurements is that it's not chemically homogeneous. So even though it seems to be one giant flow that happened at a similar time, it seems to have sampled chemically different regions in the interior of the planet. So the planet seems to be quite chemically heterogeneous in its interior. One very interesting discovery we made, I just want to mention it because it's one of those who ordered that things. We discovered a new landform that hadn't been seen anywhere else in the solar system. Science team named hollows. And these are bright deposits and impact craters. Well, no, they're within the bright deposits. They're these rimless depressions. They're these kind of flat things. And we now believe that don't have rims. They're always in impact craters. And they appear to be lost due to some sort of volatile loss. And so again, this is a sign that essentially you have some volatile component leaving the system and the materials just kind of slumping down. And somewhat similar things have been seen on some icy bodies, thought to be from sublimation of ice, but this is not an icy body. And, I have to talk about the polar deposits. Right, that was the last big thing. I mentioned these at the very beginning. These were these deposits discovered from ground-based radar astronomy and that were discovered in polar craters, and this is now the map, and the yellow indicates where the ground-based astronomy found these deposits of bright material that looked like water ice. And one of the top-level science goals in the list I showed earlier was to determine whether, in fact, these deposits really are water ice. And we confirmed that we do think they are. And there's a number of pieces of evidence we had to use. First, we had to do the imaging and laser altimetry that showed that where these deposits are regions of permanent shadow, because that's the only way ice could be permanent, could be stable on long time scales on long time scales on the surface of Mercury is if you're in a crater that is so deep that it never sees the sun. And I should mention that the rotation axis of Mercury is very, very straight up compared to the ecliptic. So there's these craters at the north, close to the pole, really are shaded. And we confirm this with imaging and laser altimetry that these craters are indeed in permanent shadow. Also, we're able to quantify, with all the data we've gotten, we were able to develop very, very sophisticated thermal models that calculate the temperatures at various points on there and confirm that where these regions, these deposits are, is exactly the temperatures where water ice and some organic materials are stable. But the key thing was actually from the neutrons. So again, going to the geochemical instruments, neutron emissions are very, very sensitive to the presence of hydrogen, since it's about the same mass. And essentially what we see is that if you normalize, what I should say is the blue is a simulation of what you would expect for the normalized signal from Mercury of neutrons, the flux of neutrons, and these are intermediate and high energy neutrons, coming out of the surface as a function of latitude, that if you assumed it was a constant composition, but you just put water ice where those deposits were observed from the radar, the blue is what you would predict for the neutron signal, and the red is what we observed. And it's quantitative perfect match, essentially. And in fact, for looking at different energy ranges of the neutrons, we can do some modeling on the thicknesses of the deposits and stuff. But this is very, very strong evidence that...
These are moderated neutrons.
Yes. Anyway, pretty clearly shows that there really are these large deposits of water ice in craters on the planet that's typically 0.4 of an AU from the sun, which is a bit surprising. This is just an interesting result that Nancy Chabot at the Applied Physics Lab did, where she basically, although they're in permanent shadow, if you look at them deep enough and basically saturate, take a very, very long image of them, there's enough scattered light off the sides of the crater that you can actually start to image the surface of these deposits. And been able to do, from this, tell that their surfaces are very young. You don't see impact craters and so on. So they seem to be, their formation seems to be an ongoing process, which is interesting. I'm out of time, so I'm really down to the last couple slides. I just want to mention that after our first year, the mission was planned for a 1-year orbital mission. It was pretty clear when we got there that we had enough fuel to extend it beyond 1 year, so we proposed to NASA almost immediately for an extension, and they gave us 1 year extended mission. And once we started that, we then proposed to NASA for a 2-year second extended mission, which we got. So in the end, we had a 4-year mission. So XM2 was our second extended mission. And one of the key things about this final extended mission was that the gravity, the evolution of our orbit due to solar and Mercury gravity was such that as we went further in time, our altitude was getting lower and lower and lower. So starting about a year ago, a little over a year ago, the beginning of our 4th year, our periapsis altitude got below 200 kilometers for the first time. So this curve was our periapsis altitude, our altitude closest approach, essentially, for the last year of the mission. And you can see is that we were very close. In fact, we had some campaigns where we got down to a few kilometers, and then we would fire our engine to come back up for a little while to keep from crashing, and so on, and so on. And until we were originally going to crash at the end of March. And so this allowed us some very, very unprecedented high-resolution imaging and measurements, and we're still analyzing a lot of this stuff. I don't show the last one. In the very end, we were able to extend the mission an extra 4 weeks by using helium gas as a propellant. We were out of fuel. We ran out of gas, but our engineers realized that we had a little bottle of helium that was used to help pressurize the various parts of the spacecraft. You realize if you blow a little helium out the back, it gives you thrust. Newton's laws work no matter what you're doing. So we were, I think, the first spacecraft to fly on just blowing helium out of the back. And it kept us going for an extra few weeks, and we got some really, really spectacular low-altitude data. This was the first image we took from Mercury orbit. This is the last image that we got down from Mercury orbit. The image resolution here is 3 kilometers per pixel. Here it's 2 meters per pixel. And so we have some chemical measurements with the X-ray spectrometer that are 2 or 3 kilometers across, and we're analyzing those right now and trying to see if we can correlate composition with specific volcanic vents and craters and things. So we have a lot of work to do now. And so I just wanted to, before I stop, just acknowledge that, of course, this is a science team of many, 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 many people. This is a picture of the science team in the control room at APL just after the spacecraft crashed. I'm actually not in the photo. I left about 5 minutes before this because I had to drive to downtown DC to be interviewed on BBC. So I couldn't be in this photo. But in any case, it's a large number. And of course, the team is larger than that. This mission is spectacularly successful, but depended on a huge number of really talented engineers, controllers, and scientists. And I'll just leave it there. It's just a very successful mission, and thanks for having me here.
Question. So you showed that vulcanized floodplain, it looked like it was coming out of the North Pole roughly. Is there any way to get an age assessment of that?
So the estimates are, the only real age assessments we can do are based on crater counting. And this is very well calibrated on the moon because there we have samples to calibrate it that we brought back and can analyze radiogenic methods. Using the calibration from the moon scaled according to modeling to what you expect the impactor flux to be at Mercury, it's estimated that those floodplains in the north are about 3.8 billion years old, and most of the older material is probably more like 200 or 300 million years older. So we think most of what we see formed within a few hundred million years, around 4 billion years ago.
So it's in the late bombardment.
Yeah, somewhere in there.
What is the percentage of iron compared to Earth?
So at the surface, it's about the surface composition of the rocks. It's on average about 1 or 2 weight percent. On Earth's crust, it's about 5, so it's a factor of a few lower. The bulk iron to silicon ratio is higher because the core is larger. But in terms of the rocky material, it's lower by a factor of 2 or 3.
So you ruled out a lot of hypotheses for the formation. Are there any left aside from the one you mentioned that was sort of ambiguous? Are there new ideas?
There's one new idea that has been published. That's really. I mentioned that there was an old idea of aerodynamic separation that you might. I didn't have the cartoon here, but essentially you can imagine you form some population of planetesimals to begin with. They get smashed up and broken into metal and silicate boulders. As those kind of fall into the sun, you could have a concentration of the metal relative to the silicate one. So that's one physical fractionation of metal and silicate model. That's old, and we haven't figured out how to test that one. There's a new one called photophoresis, which is a process I've never heard of, but it essentially is, there was an interesting paper in FJ a couple years ago where they were postulating this, that if the disk had an inner hole and mercury formed right at the inner edge of this disk, and there was dust there, that essentially the sunlight will heat up the silicate grains. It has to do with thermal conductivity, right? So I think the metal grains will heat up, but will radiate more efficiently in all isotropically. The silicate grains will heat up more on one side and get an extra radiation pressure that pushes them. So you kind of have a solar wind that would preferentially push the silicates relative to the metal. And it's an interesting idea. It's a well-established laboratory phenomenon, and they, did all their order of magnitude estimates that physicists do, but it's very hard to tell if this is a viable model. There's another model I didn't mention that that cannot explain the large core, but it may explain the different chemistry, and that's that Mercury might have just formed from materials with less ice. But there might have been the dust and rocks predecessors of the planets included materials that originally condensed in the presence of water ice. And as you get closer and closer to the sun, there's going to be less and less water ice, and it's possible. And that water ice has a lot of oxygen. So if the key chemical difference is that Mercury has less oxygen than the other, it might be a fundamental measure of ice in the very, very early solar system. So that's something people are working on, but the modeling of that shows it doesn't explain the high iron to silicate ratio. So even if that explains the chemistry, you need another thing to explain the big core. And so we don't know the answer yet, but we have data. And the thing is, of course, for 30, 40 years, people were rampantly speculating and coming up with models, and there was no way to test any of them. And now we actually have a huge data set to test any models with. And so hopefully in the next decade, we will actually get an answer.
So I know it's not your mission, but I believe Bepi Colombo is heading out there.
Yeah.
So what are they going to build on from this?
So first of all, I should say that Bepi Colombo was selected before Messenger. So it says something about NASA versus ESA, I guess. But so they're going to do a lot of the same things, but some of the things they can do better is, one, they're going to be in a more circular orbit, so they should have a better view of the southern hemisphere for a lot of these measurements. Their infrared spectrometer, we have an infrared spectrometer. I didn't talk about it all, but it only goes into about 1 to, I think, 1.5 microns. And we don't see any, Mercury doesn't show any spectral features out to there. So we weren't able to really determine any mineralogy from this instrument, but the Bepi Colombo instrument goes out into the mid-infrared, and there should be some very diagnostic spectral features. So I think the most important thing it can do is actually maybe tell us some direct information about the surface mineralogy. which we don't have. So, but that's the main thing.
Has that been launched yet? Or
No, it's been pushed back and pushed back. It's now
Okay.
January of 2017.
And then it's going to be another 7 years to get there?
Something like that. 6 years, I think. So,
Well, that's a
Well, that's an
GMT by
X-ray
then. We
image.
can't believe it.
Is it meant primarily for the surface or neosphere?
the X-ray is a surface instrument. It's again going to do the same kind of thing we did, and hopefully it will be able to fill. I don't know if you remember the maps I showed of sulfur, for example, and iron. There was a lot of empty space in the northern hemisphere, and that's because we need flares to get those measurements, and flares don't happen all that often. And we don't spend that much time over the northern hemisphere, so hopefully Mercury Colombo will really fill in a lot of the chemistry in the northern hemisphere with some spatial information. But I don't think the magnetosphere and exosphere are too weak to do anything with X-rays. But both missions have a lot of in situ plasma, mass spectrometers, and optical spectroscopy that have been used to characterize the exosphere.
Okay, well, let's thank Larry again.